Hmm. వచ్చిందా? Yeah. Friends, good evening. Yesterday I could not honor my time. Actually, I thought of taking the class. There was an exigency, there was an emergency meeting, and therefore I had to. So I'm sorry, last 2 days I troubled you. The entire schedule is disturbed. We need only today and tomorrow. For the sake of friends, maybe once again I'll announce it in the evening. Tomorrow we better take it somewhere around 11 a.m. Precisely 11 a.m. and we'll finish by 1 p.m. tomorrow. So that is the schedule, and I have completed radiation. Sorry, heat exchangers also. Now radiation is the only topic we need to cover. Before actually I go, some of the students said fins and lumped system presentations are not uploaded. If not uploaded, it will be sent today. Uh, and many of you are worried about the number of equations that we come across in convection heat transfer. At least you need to remember those popular equations, like I said, the Reddy correlation, Macadam's equation, and then a laminar flat plate, turbulent flat plate. So at least a few minimum equations you need to remember. Remaining things, so many of the expressions you need not remember. It will be given in the problem itself. Nusselt's number relation with Reynolds and Prandtl will be straight away given for a complicated system. These are like flow through a pipe. It's a very popular case in convection heat transfer, and therefore you are expected to know the Tittus-Welters equation. And the laminar flow through tubes, you remember a few of them, but not all of them. I just leave it to you. As you solve the gate papers, bold gate question papers, you will come to know what are very important, right? And going ahead with the radiation, before going with the topic of radiation, people asked me to explain NTU method once again and which type of heat exchanger is quite effective. I said the parallel flow heat exchanger is more effective. Sorry, counter flow heat exchanger is more effective than a parallel flow heat exchanger. Because in a parallel flow heat exchanger, you will never reach the maximum possible heat transfer condition. Whereas in counter flow heat exchanger, you can come across the maximum possible heat condition. Right? Now, what is that? Very quickly, I'm sorry, before actually starting radiation, I'm just talking about this. Just look at this. A parallel flow heat exchanger, THI, TH0, TCI, TC0. In a counter flow heat exchanger, THI, TH0, CI, cold inlet, cold outlet. Okay, TC0. Now here, the cold fluid inlet is the lowest temperature, hot fluid inlet is the highest temperature. We know that. That is the extreme heat exchanger. Now, there is a possibility that the cold fluid, because there is a temperature difference, a cold fluid can be heated to hot fluid inlet temperature, or hot fluid can be heated to cold fluid inlet temperature, cool to cold fluid inlet temperature. So there is a possibility of one fluid undergoing maximum possible temperature difference, and therefore the effectiveness of heat exchanger, counter flow heat exchanger, is better. Now, if you want me to draw the counter flow profile again, see the temperature difference. When you talk about, we either talk in terms of logarithmic mean temperature difference or AMTD in case theta is approximately equal to theta naught. Both the cases, Q is depending on temperature difference. Q is equal to UA LMTD or Q is equal to UA AMTD. Now, when you look at the temperature difference at all lengths of the heat exchanger, initially, of course, it's fine. For a short length, the temperature difference is considerable. As you progress through this, temperature difference between hot and cold fluids are marginalizing. And we already studied in detail, discussed in detail, that the heat transfer is a direct function of temperature difference. Temperature difference is the driving force in heat transfer. So, therefore, as the temperature difference is decreasing, in the later part of the heat exchanger, the heat transfer will not be effective in spite of the best of the heat transfer coefficients and best of the thermal conductivities of the pipes, because the temperature difference after the first half of the heat exchange are less. So therefore, heat transfers are marginally reduced. I mean, greatly reduced. They become very nominal. Whereas in case of counterflow heat exchanger, because that was clumsy and you see, always there is a considerable temperature difference, a steady temperature difference. Okay? And as the cold fluid is getting heated, it can be heated up to hot fluid inlet temperature. If the hot fluid is cold, it can be cooled up to a cold fluid inlet temperature. Whereas here it is not possible. A hot fluid can at the maximum be cooled to TCO, or cold fluid at the maximum can be heated to TH0. So therefore, the effectiveness of a heat exchanger, when I said the maximum possible heat transfer. Also, maybe I don't know how many of you understood what I said. A maximum, what is effectiveness? Effectiveness is actual heat transfer divided by maximum possible heat transfer. What is actual heat transfer? I said three equations. What are they? MH, CPH, THA minus TH0. That's equal to MC, CPC, TC naught minus TCA, heat loss by hot fluid, that's equal to heat gain by cold fluid, that's equal to UA LMTD. Any of these equations you can find Q actual. What is Q max? I straight away, those who understood or not understood, I gave the mathematical explanation. What is Q max? That's equal to C minimum into THI minus TCI. This is a standard equation. What is this? Minimum heat capacity multiplied by maximum temperature, maximum possible temperature difference in a heat exchanger. What is the maximum possible temperature difference? I have already told you. Highest temperature is THI, lowest temperature is TC. That is the maximum possible temperature. And that can be reached only in counter flow heat exchanger. Cannot be reached in parallel flow heat exchanger. So, Cmin into delta T max or THA minus TCA, that's a standard. And therefore, what is Cmin? I said the C is the capital C, whatever I am writing is the heat capacity. That C is the product of M dot into Cp. And you calculate, problem statements could be like this. Hot fluid at a mass flow rate of 0.1 meters per second is flowing through inner tube of the inner tube of a double pipe heat exchanger, and its specificity is 2.37 kilojoules per kg Kelvin. Whereas water is flowing through the annulus, its mass flow rate is 0.2 meters per second. Specifically, it is 4.187 kilojoules per kg Kelvin. So, mass and specificity of both the fluids will be normally given. And if you know both of them, you use mass of hot fluid and specific heat of hot fluid, and I call this as CH. Mass flow rate of cold fluid, specific heat of cold fluid, from the problem only. From the problem statement, you read them. So you calculate CH and CC, find out whichever is smaller, compare them. Whichever is smaller, so that you call it C minimum. Whichever is higher, you call it C max. So lower and higher are minimum and max. That's what. Now, why did someone ask me what is this introduction of NTU? I said about 4 temperatures. In order to solve the problem of heat exchanger, you need 4 temperatures. Why you need 4 temperatures? Because LMTD, To find LMTD, you need 4 temperatures. What are they? What is LMTD? LMTD is, I'm sorry, quickly I find it up. Theta naught minus theta I divided by ln of theta naught by theta I, where theta naught theta I are temperature difference at the inlet and exit, or even for a parallel flow heat exchanger, it is so. Theta I here, x equal to 0, x equal to theta naught. So that's it. Now for theta I you need this temperature difference, theta naught you need this temperature difference. So you need 4 temperatures, without that you can have calculate. I said, I gave you a procedure. If you know only 3 temperatures, you write this heat lost by hot fluid is equal to heat gained by cold fluid. What is this? MHCpH THA minus TH naught is equal to MCCpC TC naught minus TCA. And from that, if you know 3 temperatures, 4th temperature can be found. So at least you need 3 temperatures to solve this problem, so that you know you can calculate 4th temperature. If only THA, TCI are given, no way you can solve. You can neither calculate heat loss by hot fluid nor calculate heat gain by cold fluid. Then you need to come for the emissivity. Emissivity, sorry, not emissivity, sorry, radiation in my mind. Effectiveness of heat exchanger is given by these 2 equations. THI minus TH naught divided by THI minus TCI when CH is C minimum. So you're calculating heat capacities, and if you find hot fluid heat capacity is lower, then you use this equation. Effectiveness is equal to TC naught minus TCI divided by THI minus TCI in case CC is C minimum. Cold fluid has a minimum, you use this equation. In both the cases, denominator is THI minus TCI. And I told you, in no uncertain terms, I told you, you take any of these effective equations, whether CHB C minimum or CCB C minimum, you have effectiveness only 3 temperatures. You have only 3 temperatures. So if you know both inlet temperatures, if you know effectiveness, 4th temperature can be calculated. 3rd temperature can be calculated. See, in this case, if you know THI and TCI, 2 inlet temperatures, if you know effectiveness, TH naught can be calculated. In this equation, if you know THI, TCI, you can calculate TC naught if you know the effectiveness of a heat exchanger, right? So, this effectiveness of a heat exchanger helps you to find the 3rd temperature if you know 2 temperatures. And how is that you calculate effectiveness? Effectiveness is given as a function of NTU and C. What is C here? Rather C minimum divided by C maximum. Ratio of C minimum to C maximum. NTU. Effectiveness is a function of NTU and C minimum by C maximum. What is NTU? NTU comes somewhere in the part of the derivations when you solve for the effectiveness, and in the heat transfer parlance they have used NTU as equated to UA by C minimum. Okay, what is U? Overall heat transfer coefficient, how you calculate, and A of course is the surface area. Also you are very well aware that UA can be UIA is equal to U naught A naught. AI is not equal to A naught, and therefore UI is not equal to U naught, whereas UIA is equal to U naught. Either you substitute UIA or U naught A naught. But NTU is given by UA by C minimum. For the time being, don't break your heads because we don't have time. Like you assume M square is equal to HP by K. Assume that in heat exchangers, you are calling NTU as UA by C minimum. Okay, here C minimum, once again I am repeating, C minimum is the minimum heat capacity of the among the two fluids, I mean between the two fluids, and C max is the higher heat capacity between the two fluids, right? So, by knowing this equation, in fact, I have shown you what is the effectiveness equation in terms of NTU and C minimum by C maximum for parallel flow, what is for a counter flow, what is for condensation, boiling, everything I told you. So, when once those equations are available to you, effectiveness can be calculated from this equation because NTU is UA by C minimum. This is from the given parameter. C minimum by C maximum is by comparing the heat capacity. Now, only one thing I failed to explain there. Be it condensation, be it boiling, be it condensation, be it boiling, one of the fluid, hope you all can remember, this is condensation, this is boiling. There is a boiling curve. In both the cases, one curve is flat. The curve that is horizontal is indicating a phase change fluid. For condensation to happen, the vapor should be at a higher temperature, therefore the horizontal line will be higher. For boiling, low temperature liquid is boiled to high temperature. Upon addition of heat, it changes its phase from liquid. Right? Now, in both the cases, one fluid which is going along the horizontal line, the heat lost by it is not calculated by mCp delta T. For this, let me say, there is only one TH, whereas this is TCI, this is TC naught. What is the heat gained by cold fluid? If someone asks you, it is equal to mCCPC into TC naught minus TCI, right? Whereas, what is heat lost by hot fluid? Hot fluid is the condensing fluid. Now, you cannot apply this because it is not the sensible heating or cooling that's happening. It is the phase change. Phase change is always heat of QH in this case. I'm talking about this case. QH is equal to mass of the fluid multiplied by HFG. HFG is the latent heat. And latent heat, so is the case here also, heat gained by cold fluid is equal to mass of the cold fluid into HFG, whatever is the latent heat of this. So, the HFG quantity is enormously high as compared to the specific heat, and therefore the heat capacities of the phase changing fluids assumed to be much higher than the sensible heating. See, I'm talking about two fluids. One is undergoing a sensible heating. What do I mean by sensible heating or sensible cooling? A fluid without undergoing a phase change, if it undergoes a temperature difference, I call it sensible heating or cooling. What is the latent change, phase change, latent heating or cooling? The fluid will not undergo a temperature change, whereas it undergoes a phase. So, any fluid that is undergoing a phase change, in this case it is the condensing fluid, in this case it is the boiling fluid. If these fluids, the heat capacities will be enormously high because the latent heat is either coming out or being absorbed. You never know. You kept 1 kg of water on a gas stove and you started burning the fuel and the gas LPG, and till it reaches 100 degrees centigrade you can observe the phenomena. But beyond 100 degrees, at 100 degrees centigrade, slowly the water level goes down, but temperature remains at 100. But this takes a lot of time for the stove to convert this. So huge quantities of heat are associated with that. So that's what I say, the heat capacities are very high. A phase change fluid is participating in the heat exchange process, then C minimum by C maximum is approximately equal to 0. Cannot be set exactly 0, but approximately equal to 0, meaning very less. Meaning what? one fluid is undergoing a phase change, please understand. For condensation and boiling, if you are not convinced of with all my explanation, you say for condensation and boiling, C minimum by C maximum is equal to 0. Meaning C max, the fluid that is undergoing a phase change. If it is a condensation problem, C of condensation, condensing fluid, that is mass multiplied by specific, HFG. So that will be enormously, and therefore this becomes 0. So straight away you substitute this condition of C minimum by C maximum, and you get this effectiveness. Okay, so I stop the discussion here, and very quickly let me go to the radiation topic. Anything else? Effectiveness, okay. Sir, is it necessary for knowing each and every step of solution for main expression of a gate exam? See, if your mind is towards only gate examination, you are bent upon, by hearting something. I would rather at least know, if not the mathematical process, at least know step-by-step procedure right from the governing equation. See, it is such a simple subject. There is a governing equation, you take the twice, you get a solution. There is a second order differential equation, you solve for it, you get a solution. The standard procedures are applied. So, at least you know that step by step, what is that I equate, what is the governing, where do I start, whether I integrate or differentiate, and whether I substitute the boundary conditions or not. If so, what kind of a boundary conditions that I substitute, and from this, what is that I get? You have only two solutions. One is either you get a temperature distribution equation or heat transfer rate is equal to. So at least know the step by step. Okay. So I just don't say much more than that. The hot object in vacuum chamber will eventually cool down and reach a thermal equilibrium with the surroundings by heat transfer mechanism or radiation. Meaning, you keep a hot object in an evacuated chamber, no fluid there. When there is no fluid, it's perfectly evacuated. There's no convection heat transfer, because convection heat transfer is because of the bulk motion of the molecules. When there are no molecules at all, no convection. And is there a conduction between the hot object and the enclosure chamber? No, because there is no solid connected. Still, after certain time, you find that the hot object loses its temperature and chamber gains the heat from the hot object. So that obviously means that radiation doesn't require a mechanism. In fact, while giving you the examples at the very beginning, I said, giving an example, a piece of chalk, how it can be transferred to the last person. Okay, everyone sitting without moving, only hands moving, it can, or everyone come to the lecturer and pick a piece of chalk and go, or lecturer can throw his chalk to everyone. So the third category is radiation. Radiation actually doesn't require a medium. Yeah, it can throw, the radiation can be transferred even in the vacuum. That's the point I wanted to say. Radiation definitely differs from conduction and convection. It doesn't require a material, because the mechanism of conduction, are very, very clearly defined. Now you are very clear how conduction heat transfer takes place. Molecular momentum exchange and also drift of free electrons. And how convection heat transfer takes place. Is it because of natural convection or force of convection? Unlike conduction and convection, heat transfer by radiation can occur between two bodies even when they are separated by a medium colder than both. This is another important observation that you need to make. See, I am at say 36 degrees centigrade. Let me say the monitor, because of the heat release, it is at 40 degrees centigrade. There's a temperature difference. Now I am throwing some radiation towards the monitor. Monitor is throwing some radiation towards me. And in between, separating us, there is an air medium. I am in an air conditioned room. The temperature is somewhere around 25, 26. In spite of having a colder medium in between us, still the radiation exchange is comfortably happening between the two high temperature bodies. They ignore as if a cold medium is available here. Okay? So that's how it happens. And two ways people explain this. People say that radiation is exchanged in the form of electromagnetic waves, or it is also called as electromagnetic radiation. And when I'm talking about waves, you talk about wavelength, you talk about frequency of the wave, and also speed of the wave. So all these three parameters, you keep talking about it. Fundamentals of your physics. Okay, very fundamental physics tells you the wavelength is equal to speed of the wave divided by the frequency with which it oscillates, right? And there are certain parameters like the speed of propagation of a wave in the medium, the light wave or the radiation wave. C naught is the speed of light in vacuum, and it's a standard value. I said close to 3 into 10 power 8 meters per second. And normally someone talking about centimeters, 10 power 10. Okay, n index of refraction of the medium, and C is equal to C naught by n. And again, these are all very fundamental physics. Very fundamental physics. Yeah. The refraction index of air is 1, almost nothing, and for water it is different. For glass it is different, and that's why depth of water appears shallow. Some very fundamental physics cases. A coin dipped in water appears to be at a smaller depth, but when you actually immerse your hand, you find it at much deeper length. Okay, so all this, the refractive index. Now, it has proven useful to view electromagnetic radiation. Sometimes it is also explained as the propagation of discrete packets of energy. If someone is throwing energy packets by virtue of his surface and by virtue of his energies, and these pockets are called photons or quanta, and these energy transmitted is explained in terms of E equal to h nu, where h is a Planck's constant, which is a universal constant 6.626 into 10 power minus 34 joule second. And nu is, of course, your frequency of the wave, which can be obtained when you know the speed of the wave and its wavelength. So the amount of energy transmitted because of this radiation, by the radiation heat transfer, it is again depending on the wavelength and the speed. We are going to discuss all of that. So be it an electromagnetic wave or quanta of energy thrown is equal to E is equal to h nu. Okay. So here, when I'm talking about radiation, in fact, I spoke to you about all this. The radiation spectrum is quite huge, at least from 10 power 10 to 10 power minus 10, 10 power minus 10. See, such a huge bandwidth of micrometers, 10 power 10 micrometers to normally the other way you express it in angstrom units, right? So, again, physics. So don't worry if you don't understood that part of physics, don't worry too much, but we use only limited knowledge there, but it's always good to know the fundamentals very good. Okay. Now, I told you that I was always talking to you. Look at the cursor. I don't know whether you are viewing the cursor. The visible spectrum in a wavelength range of 10 power 10 to 10 power minus 10, the visible spectrum is quite narrow. How much? 0.38 micrometers to 0.78 micrometers. Could you see it here? 0.38 to 0.78. Okay. In the thermal radiation is somewhere from 0.78 where the visible spectrum ends. 0.78 stands for red wavelength. 0.38 stands for visible wavelength. Below that it is ultraviolet and above this it is infrared. And most of the thermal radiation is emitted in terms of infrared when in the wavelengths of infrared, and therefore most of the radiation emitted by a surface you cannot see it. You cannot see it. See, I told you any surface by virtue of its surface temperature, that's what it is. Thermal radiation is continuously emitted by all matter whose temperature is above absolute zero. Any temperature above absolute zero, and also your thermodynamics formula says reaching absolute zero is practically impossible. It's impossible. But any surface having a temperature other than absolute zero can emit radiation. My body is emitting radiation right now. The shirt is emitting radiation. The monitor is emitting radiation. The desk, the curtain, everything are emitting radiation. Yep. But you cannot see them. Why can't you see it? When there is something coming, people say, solar radiation. You can see solar, you can visualize solar radiation. Right? You can distinguish. When a cloud cover is there, it is something. When cloud is not there, it is something. But absolutely you have no clue how much radiation or whether you are emitting radiation or not also. So, the point I am clarifying is the radiation emitted by, virtue of the temperature of a surface is mostly into thermal radiation. And of course, beyond that, you have microwaves, now microwave heating, microwave oven is altogether a different concept. And then you talk about radio waves, TV waves, when you come down, ultraviolet, X-rays, gamma rays, cosmic rays, and of course, all this. I have many interesting stories to tell you, but definitely this is not the time I tell you stories, right? Now, solar radiation. Look at here where the cursor is placed. The electromagnetic radiation emitted by the sun is known as solar radiation, and nearly all of it falls into wavelength band 0.3 and 3 micrometers. See, entire solar radiation or majority of the solar radiation is in the wavelength of 0.3 and 3 micrometers. What is visible spectrum? I said visible spectrum is between 3.38 and 0.78. What is below 0.38? It is ultraviolet, right? So, majority of the solar radiation is between ultraviolet is from ultraviolet to 3 micrometers is infrared. Because only up to 0.78 you have red. Beyond 0.78 it is infrared. So when I say majority of the radiation, don't say that entire solar radiation falls in the spectrum, but majority of the solar radiation falls in the spectrum. Almost half of the solar radiation falls into visible rays. What is that? Between 0.3 and 3, only you have 0.38 and 78, right? How 50% of the solar radiation falls in between 0.3 and 7. So essentially, I would say the solar radiation is a short waveform radiation. Whereas, I just need to bring your attention. Look at it. 50% of the solar radiation falls here, and remaining things also, it is marginally on this side and marginally on this side. Whereas thermal radiation is ranging up to 0.78 to 100 micrometers, whereas solar radiation ends at 3 micrometers. So, I would say, as compared to thermal radiation, I need to tell you why I am explaining so, but then I need to explain to you an important thing. So, the solar radiation, 50% of it fall in this narrow wavelength range of 0.38 and 78. But between 3 and 0.3 and 3 micrometers, almost everything is there. Okay, that's solar radiation. Whereas half of the solar radiation is there. Now, the radiation emitted by bodies at room temperature falls into infrared region. Even at room temperature, anything that is emitting radiation, they are all infrared radiation. You cannot see them. The ultraviolet radiation includes low wavelength radiation, and that is the end of the thermal wavelength spectrum and lies between 0.01 and 0.4 microns. 0.4 microns. So ultraviolet rays are to be avoided since they can kill microorganisms. Have you ever seen UV, cleaners? Okay, UV treatment can be given. That can kill all the germs. So microorganism is killed. Your ultraviolet radiation is very dangerous. Now, in view of the COVID, you have UHS also, right? So this dangerous part of the radiation, fortunately, is being filtered at the ozone layer. Ozone layer is the top layer on the top of atmosphere, right? So you all know, just Google what are all the layers you have above the atmosphere, then you will come to know. Ozone, you find it on the top layer, right? So 12% of the solar radiation in the ultraviolet range. Fortunately for us, the solar radiation within the this 12% of solar radiation is being filtered right on the top, right on the top. So when 12% is gone, only 88% of solar radiation is coming into the Earth's atmosphere, is being allowed. Something is being filtered there. That's how ozone protects us. Everyone is talking about ozone layer. And don't, ever get confused between the ozone layer and global warming. Everyone very clumsily, you confuse, get confused among all this. So ozone is a layer which can filter ultraviolet radiation. Meaning what? The ozone layer, ozone gas, has an exclusive property for radiation, such that they are highly opaque to short waveform radiation. They are highly transparent to long waveform radiation. What do I mean by that? Any wavelengths in the by ultraviolet radiation and below, like X-rays, etc., they cannot penetrate through it. They cannot largely penetrate through it. They are often filtered there, and remaining radiation beyond ultraviolet, they are allowed to go. Now, what is this ozone layer people are talking about? There was a situation where we were using refrigerators, and the working fluid in refrigerators, we call it refrigerants. I'm sure all of you know. There was a stage till late 1980s, difluoromethanes or chlorofluorocarbons were used. This fluorine and chlorine, the refrigerants, when they are released into atmosphere, when they are split into chlorine and fluorine, being lighter, they can vertically move up to ozone layer. Now, what happens in ozone layer? Ozone is O3, all of you know. And if you are thinking that ozone layer has plenty of O3, you are partly correct and partly not correct. Because it has O3, but it is a continuous reversible chain reaction, reversible reaction. O2 and nascent oxygen molecule, they come together to form into O3. O3 unstable, it splits back into O2 and O. See, this is a continuous reaction that's happening. So O2 and O all the time, they come together and forming into O3. Now, if a chlorine and fluorine go there, they have a great affinity to nascent oxygen. Cl go, attached to nascent oxygen. Another Cl will go attached to nascent oxygen. The ClO come together, and Cl gets separated, O2 gets separated. So nascent oxygens are all converted into O2, and fluorine also does the same. So one chlorine or fluorine atom presence there will consume millions of the nascent oxygen molecules. That's how a reversible reaction is prevented. O2 reacting with nascent oxygen, forming into O3, is now stopped because all the nascent oxygen, these are getting attached to it, and they're not stopping there. Again, they are coming together. These two nascent oxygen molecules are coming into O2, and effectively they're bringing the two nascent oxygen molecules and converting them into O2. That's how the reaction happens, and therefore people are talking about hole in ozone. No, because of the excessive release of chlorofluorocarbons. Even in the puff refrigeration, puff insulation I was talking to you, even puff uses chlorofluorocarbon as a catalyst. So somewhere when they are released, they vertically move up. They kill the ozone layer. So technical or activity, man-made activity, when chlorine, fluorine are released, now they'll go and destroy the ozone layer. When ozone layer is destroyed, meaning you are allowing ultraviolet radiation to come into the atmosphere. Okay, so let me not be more detailed than that. In heat transfer studies, we are interested in energy emitted by bodies because of the temperature. Therefore, we limit our consideration to only thermal radiation. We limit our consideration to thermal radiation. And even in the Earth's surface, the water molecule, water vapor, absorb the infrared radiation, and therefore even infrared radiation is filtered, and solar radiation is coming. And I said 0.3 to 3. Water vapor absorbs some part of infrared radiation. Very effectively, UV is filtered there at the ozone layer. Very effectively in the visible spectrum, you get the solar radiation. That's why you could feel the bright sunshine. Okay, you can feel the sunshine, and the solar radiation is slightly different from thermal radiation. I'll explain why it is. Now I'll explain the global warming also. Now, this short waveform radiation coming from the sun, after getting filtered, UV being filtered, infrared being absorbed by water vapor, whatever is remaining is traveling towards the earth and it strikes the surface. It hits a road, it hits a building, it hits your car, it hits your bike, and it heats everything because energy is being given them. Radiation is being absorbed by these surfaces. And when the energy is absorbed, the surface temperature increases. When the surface temperature increases, now they emit radiation. The emitted radiation is long waveform radiation. Emitted radiation is long waveform radiation. That's what I said, thermal radiation. Whereas solar radiation is short waveform radiation. Now what am I saying? The solar radiation coming is short waveform. Short wave radiation. Short wavelength. And they are striking the surface, hot they become hot, and the hot body is emitting, by virtue of surface temperature, is emitting radiation. This is emitting thermal radiation. This is what I call it as thermal radiation. This is solar radiation, right? Solar radiation. The thermal radiation is long wave. Long wave in the sense beyond 0.8. This is almost limited to 1 micrometer. This is beyond up to 100 micrometers. The radiation emitted is 100 micrometers. Now, what shall happen normally? Once again, I draw it here. The solar radiation is coming, hitting a surface. The radiation is converted to thermal energy, by virtue of which surfaces get heated. The heated surface emit radiation, and they must be escaping into space. They must be literally escaping into space. Now here happens some other phenomena. This phenomena is called global warming and greenhouse effect. What is this greenhouse effect? They accumulate certain layers of gases like methane and carbon dioxide, which we plentifully release. Agricultural based country like India, and where a cattle population is there, plenty of methane is released. And methane is CH4. And CO2, we're all involved in such a foolish experiment, as if it's a laboratory experiment. We're all involved in such a foolish activity. Wherever it is possible, we burn either coal into fire and then convert it to carbon dioxide. We burn LPG and release into carbon dioxide. We burn petrol, convert into carbon dioxide. We take diesel somewhere it is there under the earth's crust. We dig it out, pump it out, and then burn it, release carbon dioxide. So we are releasing a lot of carbon dioxide. So these carbon dioxide and methane kind of gases, these are called global greenhouse gases. These greenhouse gases, when they are accumulated in the Earth's atmosphere, these greenhouse gases are highly opaque to long waveform radiation. They are highly opaque to long waveform radiation. What do I mean by that? What do I mean by that? On the Earth's surface, solar radiation is coming. There are, layer of greenhouse gases, let me say. Greenhouse gas, GHG. Now, the solar radiation being smaller waveform, they can easily pierce through, penetrate through this, meaning they are transparent to short waveform radiation. They allow the radiation to come in, short because it is short wave. The radiation is striking the Earth's surface. They are converted into thermal radiation. I told you thermal radiation is between 0.1 and 100 micrometers. Okay, whereas this is between 0.3 and 3 micrometers. So smaller wavelength can penetrate here on this side, very easily come here. And when they strike the surface, the temperature is increased by virtue of the surface temperature. They emit radiation. The emitted radiation is thermal radiation, long waveform. This long waveform would like to escape into the sky, but this greenhouse layer prevents it from going, and it says, please, you cannot go back, please get back. So, it's one-way traffic. Entire solar radiation is coming onto the Earth. It is striking a road, it is striking a building, it is striking you, it is striking your car, and energy is absorbed by these surfaces on which it is falling. They get heated up, they emit radiation. Emitted radiation is long wave, and this long wave form radiation would like to escape, thermal radiation would like to escape into sky. Here comes the culprit, greenhouse gas, which says, sorry boss, you cannot go through me, you get back. So it sends back anything. So that way, kind of a thing. Radiation comes from the sun, and emitted radiation otherwise would have escaped into the sky is now prevented from going. That means what? Energy is accumulated here, and global warming takes place. Meaning, atmospheric temperature rises. It's a very simple thing. See, I have some radiation coming, some other form radiation, some other. Thermal radiation is energy, right? So something is coming, something is going back, it's fine. But what is happening? I'm putting a layer here. This is again man-made layer. This is man-made layer. Carbon dioxide levels in the atmosphere is, when you compare to French Revolution, the present carbon dioxide levels in atmosphere is double that of the carbon dioxide levels just before French Revolution. You all know French Revolution is also called as Industrial Revolution. So when you started going mechanized, you wanted energy to drive all these machines, and you started taking out coal, converting it to carbon dioxide. You started taking petrol, diesel, converting it to carbon dioxide, and you started, taking gases and converting them into carbon dioxide. You started burning wood and converting them into carbon dioxide. Any combustion reaction of any fuel, any carbonaceous fuel, other than hydrogen, hydrogen reacting with oxygen gives H2O, pleasant for us. But any carbonaceous fuel or hydrocarbon, where carbon atom is there, essentially it has to undergo oxidation reaction with oxygen and combustion reaction and forming into CO2. CO2 is exothermic, that's how calorific value is released. Okay. Now the man-made activity is causing more and more carbon dioxide to be released. They are accumulating here, and therefore it's not allowing the gas to go. Now, on top of it, what is that you are doing? There used to be lush green tree cover all over the earth, wherever water was not there. And now you started cutting them because you need to develop your own dwelling habitat, and you started cutting the trees of the forest. And what is happening when you are cutting the trees? The tree population is reduced, and these trees absorb carbon dioxide in the photosynthesis reaction. All of you know. And had the trees been there in plenty, probably they would have absorbed. They had been absorbing carbon dioxide. Now that on one hand you are releasing more carbon dioxide, on the other hand you are cutting the trees, and therefore it's a cumulative cascading effect. You are releasing more carbon dioxide, and you are cutting all those trees which used to absorb carbon dioxide, which are absorbers of carbon dioxide, and therefore you are accounting for more and more carbon dioxide. Therefore, the energy is solar energy is coming, whereas it's not going back into the space because of this. Any thermal radiation is not able to go, and that's what is called global warming. Global warming and ozone, they are two different things. Don't get confused. Okay, greenhouse gases, greenhouse effect. What is greenhouse effect? This greenhouse gases allow short waveform radiation to come in, and they will not allow long waveform radiation to go. Maybe many of you must be aware of the solar water heaters, right? They have a glass cover on the top. Why do they use glass cover? When solar radiation comes, glass is transparent to short waveform radiation. This can penetrate through the glass cover, hit the absorber plate, get heated. When heated energy is released, emitted as a thermal radiation, that cannot escape because glass is opaque to long waveform radiation. This is also the greenhouse effect that we have manually created. Okay, so all these greenhouse gases, global warming is because of the presence of greenhouse gases, and the effect is called greenhouse effect. Okay, so I'm sorry I had to detour, but I just wanted to tell you all this. Okay, now, so gas vacuum radiation will be emitted, and it can be emitted for all directions. Okay, it can be emitted in all directions. So we what we call it as specular radiation in opaque bodies is considered as a surface phenomena, since the radiation emitted by the molecules at the surface can escape the solid. So opaque bodies, it's purely surface phenomena. For rest of the things, it is a volumetric phenomena. Meaning something happens within the solid, within the microscopic level, or the atoms and molecules of all solids, they can contribute to some energy release. A few kind of solids, except for opaque bodies, the radiation for all opaque bodies, radiation is purely surface phenomena. Meaning what? This is a opaque body. I don't know what is happening beneath. No, it purely depends on what happens at the surface. What is the temperature of the surface? And from there, the radiation. Few are volumetric phenomena, few are surface phenomena. Please make a note. And I've already told you what is an idealized body called a black body. Black body is one which absorbs all the radiation falling on it, irrespective of the wavelength. I said the wavelength can be from 10 to power 10 radio waves to cosmic rays. All this radiation shall be absorbed by a black body. Black body, there is no exception. It cannot allow it to pass through. It cannot reflect it. It shall absorb entire radiation. That's an ideal body. And also a black body is a perfect emitter. It's a good absorber and a perfect emitter. No other body can emit equal amount of radiation than that of a black body when both are maintained at the same temperature. When both the surfaces are maintained at the same temperature, black body is one which invariably emits higher amounts of radiation. And also when you talk about absorbing capacity of the incoming radiation, some radiation from somewhere it is coming and it is being absorbed, completely it is being absorbed by the black body without any exception, regardless of wavelength, regardless of direction. Is it coming from this direction? Is it coming normal to the surface? Is it coming from tangential direction? Anything that falls on the surface. So for a black body, radiation emitted is given by Stephen Boltzmann's law. Emissive power of a black body, of course, per unit area, watts per meter square, is sigma T power 4. And if you want QB, it is sigma A T power 4. See, heat flux, radiation flux emitted. Okay, sigma A T power 4. And again, let me tell you, in all these radiation calculations, you are using temperature in terms of Kelvin. You are using a temperature in terms of Kelvin. So, a Stephen Boltzmann's constant, of course, let me not take time, is sigma is equal to 5.67 into 10 power minus 8 watts per meter square Kelvin per hour. Now, I seriously request all my friends to remember the units of every parameter that you are using. Okay, that helps you avoid confusion. Otherwise, you are greatly confused because there is a heat flux, there is a heat transfer, there is thermal conductivity, there is heat transfer coefficient. Okay, there are many things you come across. Okay, so you normally get confused. There is a thermal resistance, there is a thermal conductance. So there is a overall heat transfer coefficient, there is Stephen Boltzmann's constant. So you get confused. A black body phenomenon normally is explained like this. If you have a cavity, a large cavity, on top of it you make a small aperture, a small hole, and allow the light to pass through it and try to observe whether you can see the light. Unless, when can you see a surface or light? When something goes and falls on it and strike back, you come back to your eye, then only you can see. They say the time required for the radiation to travel, light to travel between sun and earth is 8 minutes or so. So you can only after sun appears, you can see it only after 8 minutes or so. See, that's it. So unless you see, why in dark you cannot see? Why in dark you cannot see? See, in the midnight, when you got up from your bed, you can't see anything because every object is there still. But some light is not falling on it, and the object is not reflecting its radiation from its surface. And unless some light is coming from the surface, you cannot see it. You cannot see its color, you cannot see its boundaries, you cannot see its shape. So unless something comes out from a surface, you cannot see it. Now, in a small aperture, when you throw some light, the light gets multiply reflected within it. It undergoes multiple reflections, and on each falling on the surface, some radiation is absorbed. Slowly, the intensity of radiation is died down, and therefore you don't see anything. That means black body is one. Okay. The spectral black body emissive power is given by Planck's law. What Planck's law says, the monochromatic emissive power of a black body, again, let me not confuse you. The monochromatic emissive power is emissive power of a black body at a given wavelength. Monochromatic means at a given wavelength. Whenever you talk about EB lambda, you mention a lambda. At what? Is it at 0.1 micrometers? Is it 0.5 micrometers or some other micrometer? Okay. So the monochromatic emissive power of a particular lambda and wavelength temperature. No, it varies with, it is a function of lambda and temperature. That's what it says. And any radiation emitted by a black body depends on the wavelength of radiation it is emitting, wavelength at which it is emitting radiation, and also the temperature of the surface. And he has used the wavelength and two constants called C1 and C2. And C2 uses a constant called Boltzmann constant. Its value is given there. The C1, C2 values are constants. You may remember it because, quickly there may be a problem. And you need to remember Planck's constant, Boltzmann constant, C1 and C2 of Planck's law, if at all, if it is possible. That's always advisable. So if you know C1, C2 values, if you know wavelength, if you know the temperature of the surface of a black body, remember this is only for a black body. It's not for a non-black body. Okay, so you can calculate this. And it says the variation of EB lambda, the variation of EB lambda with the temperature. That's what you know. EB lambda is a function of temperature and lambda. That's what Planck's law says. Okay. When you know lambda, you know temperature, you can calculate EB. Okay. So what is that you need? You need to calculate MC power, you need a wavelength and also you need a temperature. For different temperatures, they have plotted this curves. So the EB, MC power of a black body, what Planck's law says is, when you plot for a particular temperature, say 100 Kelvin, for different wavelengths, when you start calculating, at 100 Kelvin, the first radiation emits. The radiation emits only at, say, somewhere around 70 micrometers, and before that, any wavelength shorter than that, no radiation is emitted. Okay, that's what it is. So from 7 micrometers up to say 1000 micrometers, radiation varies for a black body. And also it is said, Planck's law says, the radiation, as you increase the wavelength, the emissivity power of a black body increases, reaches a maximum. For a particular wavelength, radiation will be maximum. And as you further increase the wavelength, it will move towards the left. The emissivity power of a black body reduces. Meaning, at 100 micrometers, at 100 Kelvin, this is going to be the emissivity power. So, what is this? At 50 micrometers, at 100 Kelvin, you have a maximum, let me say. Similarly, when this experiment is repeated for different temperatures, now this time you make the surface to be at 300 Kelvin. And again plot. When is the first time for the first wavelength where the energy started emitting from the surface? You are measuring radiation coming out from the surface at all wavelengths. You are calculating, you are measuring. So, again the same trend is noticed. Initially, it starts at some short wavelength. As the wavelength is increased, EB maximum reaches and then it falls down. So for different temperatures, the same phenomena is observed. That is what Planck's law talks about. What is Planck's law talking about? Planck's law talks about this. What is it? At a given temperature of the surface of a black body, don't forget, Planck's law talks about only black bodies. At a given surface of a black body, it has a wavelength range between which radiation is emitted. In this case, in 100 Kelvin, it starts at somewhere around 7 microns, ends at 1000 microns. Whereas at 300 Kelvin, the radiation emits at say 2 microns and ends at 1000 microns. So every temperature has a wavelength range between which the radiation is emitted, and every temperature has one particular wavelength at which radiation is emitted is maximum. These two things Planck's law talks about. Now, Wiens is a scientist. Wiens is a scientist who has noticed a peculiar phenomena in this plots of Planck's law. He says, no, he only observed the peaks. What do I mean by peak? Wherever EB lambda maximum is happening, meaning EB maximum amount of emission is occurring and a wavelength corresponding to that. Not wavelength is maximum. Don't get confused. Not wavelength is maximum. It is that wavelength where emissivity power is maximum. So, this is the wavelength here, and this is the wavelength here, this is the wavelength here. So, for every surface temperature, there is one wavelength at which a black body is emitting maximum amount of radiation. Maybe in one case, say 50 micrometers. In another case, it is only 5 micrometers. In another case, it is only 0.1 micrometers. And he has understood, interestingly, that as the temperature is increasing from 100 to say 5800, average temperature of sun is said to be at 5000 Kelvin, 5800 Kelvin. So as the temperature is increasing, the maximum emissive power occurs at one particular wavelength, and that shifts towards the left, meaning towards the shorter wavelength. As the temperature is increased, the wavelength at which the maximum power occurs is shifting towards the left, meaning as you increase the temperature, maximum emission is happening at smaller and smaller and smaller wavelengths. This is what is Wien's displacement. And look at it. Don't get confused. The peak is here, peak is here, peak is here. Peak is moving towards the left. The dotted line indicates the path of the peak. Peak is moving towards the left. The left is towards smaller wavelength. And of course, the various visible spectrum and violet and ultraviolet, everything is spotted there. So, as the temperature increases, it is moving towards shorter and shorter wavelengths. Wien's displacement law is lambda T max, and maximum power where it is occurring. That lambda, where I'm talking about, I don't know, how can I point? This lambda, this lambda, this lambda, this lambda. A lambda corresponding to all peaks. Lambda, where maximum EB is occurring, multiplied by the temperature of the surface. Very interestingly, because wavelength is when temperature is increasing, wavelength is moving towards shorter wavelengths. So they are inversely related, right? So lambda T means display, Wien's found it to be a constant value called 2897.8 micrometer Kelvin. So lambda T max, lambda T, meaning not all lambdas. Lambda where the maximum emission power is taking place multiplied by the temperature of the surface is always constant. That's what Wien's displacement law is. Can I break for say 5 minutes and get back? Thank you very much. You are presenting and minimize. Okay. So, some of those observations that we can draw. The emitted radiation is continuous function of wavelength. At any specified temperature, it increases with wavelength, reaches a peak and then decreases. No, that's an inverted dome. Dome kind of structure. At any wavelength, the amount emitted radiation increases with increase in temperature. Both are established. And shorter wavelengths, the peak is shifting towards shorter wavelengths. Radiation emitted by sun, which is considered to be a black body at 5780. Sun is considered to be a perfect black body. Therefore, it reaches a peak in the visible region of spectrum, and therefore sun is visible to you. Okay. On the other hand, surfaces at temperature less than 800 K. Would you like to go through this? Yeah. At the temperature less than 800 K, it's all in the beyond the visible spectrum. It's all beyond the visible spectrum. Where is visible spectrum? Only up to 0.78. Okay. So, temperature less than 800 K emit almost entirely in the infrared region, and thus they are not visible to the eye at all, unless they reflect light coming from other sources. The objects, all that you are seeing, you are not seeing them by virtue of the radiation emitted by them. When light is, that's what I said, in the night, they all become dark. When radiation goes, falls and it comes back to your eye, then, they're visible. Meaning, they're not emitting radiation on their own, and they must be emitting, but you cannot see that. What is that you are seeing? Some other light is coming and falling on it, which is reflected by the surface, which is catching your eye. So, therefore, that's it. Okay. So, MCU power at a particular of black body at a particular temperature is integration of all wavelengths. It starts from some wavelength and it's going at some other wavelength. Over the entire wavelength radiation, at each wavelength, what is the amount of radiation emitted? Which we called it already monochromatic MCU power. This is called monochromatic MCU power. Okay. So, at all wavelengths, it is emitting. You add all the radiation emitted at each and every wavelength, and you get the total one. That is equal to sigma T power. That's equal to sigma T power. And incident light may have red, yellow, green, and blue, and the wavelengths. Let me say. And if the material has a capacity to absorb yellow, green, and blue wavelengths. And already you must have understood by now, looking at ozone layer, looking at greenhouse gases, looking at how the surfaces behave, every surface behaves differently, but different wavelengths. Some surfaces absorb short wavelengths. That's why I said, snow is close to a black body, but it reflects all the radiation in the visible spectrum, and therefore all the wavelengths mixed together form white to your eye. Form white to your eye. Okay, so they will come. Now this surface, when you see, if incoming radiation, incident radiation consists of red, yellow, green and blue wavelengths, if it is capable of absorbing yellow, green and blue, if it is absorbing, and it is capable of reflecting only red, that surface appears red to you. Because something is falling on it, something is falling here, this part of the surface is absorbing all other wavelengths, but it is reflecting red. So therefore, only red wavelength is coming out of it. That is falling your eye, and therefore you see it as red. What do you see it as white? If all the wavelengths mix together and come and fall on your eye, you feel white. So therefore, white is a perfect reflector. That's what they say. And therefore, in summer like this, you should wear only white clothes. White clothes because they reflect a lot. They reflect a lot. And black means they absorb a lot. And I ask you a question, I don't explain because I know I don't have time. Then why in olden days the umbrellas had only black cloth? You wanted it to absorb more heat and then boil your head? There's some logic, you please think about it. Okay. So this chart, of course, you have already seen. Surface that reflects red while absorbing the remaining parts of the incident light appears red to your eye. That's what I said. And if something is absorbing all of the wavelengths and reflecting only blue, it appears blue. Okay. Radiation intensity, and of course, all these geometries you can see in any textbook. And radiation intensity is denoted by I. It is defined as the intensity of radiation is defined as the rate of energy leaving a surface in a given direction, in any particular direction, per unit solid angle per unit area of the emitting surface normal to the mean direction in the space. Unit solid angle per unit area of the emitting surface. Emitting surface, if my hand is empty, it has a surface. This is what I mean by emitting surface, because radiation is emitted from this. Okay. Okay. Energy of leaving surface is given a direction per unit solid angle per unit area of the emitting surface normal to the mean direction in the space. Okay. So mean direction in the space, it is normal to the surface. What is a unit solid angle per unit solid angle per unit area normal to the surface? Fine. Okay. What is a solid angle? Every one of you know. Solid angle is defined as, no, come back here. It is the conical angle that is subtended at the center when on the top of the sphere it is occupying area of dA, let me say. Okay. So it's a cone subtending an angle at the center of the sphere. So a solid angle is subtended by complete hemisphere. Is that particular area covered by this cone on the surface of the sphere. It's almost circle 2 pi r square and divided by the radius square, the distance from the center to the surface. So normally the solid angle is given by 2 pi. So intensity of radiation is the amount of radiation emitted normal to the surface per unit solid angle. And this Lambert's cosine law is very, very important. And before that, the relation between intensity and mc power of a black body, both are for a black body. Mc power of black body is pi into Ib. Okay, intensity of a black body into pi is equal to mc power of black body. And Lambert's cosine law, E theta is equal to E normal, in the sense normal to the surface. A surface can emit radiation in all 360 degrees, and if you calculate what is the radiation emitted normal to the surface, intensity when you calculate, IN multiplied by pi will give EN, and if you know EN, and if you know theta, En cos theta is E theta. Okay. Certain properties, someone asked me at the very beginning, what is the emissivity for radiation? Okay, I leave opaque and transparent, semi-transparent, all of that, fundamental physics, Emissivity, if you have two surfaces, see, look at my two palms. One is a black surface, let me say, another one is, a real surface, other than a black surface. And the amount, it is the ratio of the radiation emitted by a real surface, by a given surface, to that of a black body when both are maintained at the same temperature per unit area. Both are unit areas and both are maintained at the same temperature. We know that a black body is the one which emits maximum amount of radiation, whereas a real surface cannot emit the equal amount of radiation. So it is the ratio of radiation actually emitted from a real surface to that of radiation emitted by a black body. Okay, so if you have two black bodies kept side by side and both are maintained at the same temperature, because both are the same surfaces, amount of radiation emitted by both of them is equal and the same, and therefore the emissivity of a black body is equal to 1. Because what is emissivity? Radiation emitted by a surface to that of radiation emitted by a black body when both are of unit area and the same temperature. Okay, so we also know that any surface other than a black body cannot emit equal amount of radiation. Any surface other than a black body cannot emit equal amount of radiation. So, the emissivity for any real surface is always less than 1. Emissivity of any real surface is always less than 1. Emissivity of a black body is equal to 1. Okay. Emissivity of a real surface varies with the temperature on the surface as well as wavelength as well as the direction. Okay. Meaning what? If you are talking about a black body uniformly emits radiation in all the directions and it emits in all wavelengths. Okay. In all wavelengths. Whereas this is a black body. Whereas a real surfaces, certain surfaces can emit radiation only in a particular direction. Only in a particular. Real surfaces can emit only in a particular direction. That is called directional emission. And in a sense, this real surface is not good at emitting radiation in this direction or tangential direction. Certain real surfaces are very good in emitting in the normal direction. Vertical. So, directional variation is there, and also certain real surfaces, let me say they emit maximum amount of radiation is 0.1 micrometers. Whereas certain other surfaces may emit maximum amount of radiation only at 0.2 micrometers. Okay, and also the same surface, it emits different at 0.1 and different at 0.2. So, directional sensitivity, directional variation, as well as wavelength variation. At every wavelength, it is behaving differently. Okay. Now, when I talk about radiation, emissivity, I talk about emissivity N, emissivity theta, and emissivity lambda. What is it? Normal emissivity means I have a real surface, I have a black surface. How much of radiation is emitted in the normal direction to the surface, and both are maintained at the same temperature. And how much of radiation is emitted by real surface? I don't use B here, EM I call it. So, real surface normal ga enta radiation emit chestundi, black body normal ga enta radiation emit chestundi. Then emissivity N is equal to EN divided by EBN, meaning normal direction వచ్చే radiation ratio మాత్రం తీసుకుంటే you call it emissivity normal. And directional, at a particular direction, say at a particular theta angle when you're measuring, and you call it E theta, and you, for this for a real surface, you call it for a black surface, EB theta. So therefore, emissivity theta is equal to E theta divided by EB theta. Okay. So, ఒక పర్టికులర్ డైరెక్షన్ లో ఎంత రేడియేషన్ రియల్ సర్ఫేస్ ఎమిట్ చేస్తుంది, అదే డైరెక్షన్ లో హౌ మచ్ బ్లాక్ బాడీ కెన్ ఎమిట్ రేడియేషన్ వెన్ యూ గో ఫర్ దిస్. వాట్ ఈస్ మోనోక్రోమాటిక్ ఎమిసివిటీ ఈ లాంబ్డా? దిస్ ఈక్వల్ టు వాట్ ఈస్ ద రేడియేషన్ ఎమిటెడ్ బై రియల్ సర్ఫేస్ అట్ ఎ వేవ్ లెంత్ లాంబ్డా. లాంబ్డా అనే వేవ్ లెంత్ దగ్గర ఎంత ఎమిట్ చేస్తుంది? సారీ, so this surface is real, this surface is black. At a particular wavelength, lambda is equal to 0.2 micrometers అనుకోండి. At 0.2 micrometers, how much a black body is emitting, and at 0.2 micrometers, how much a real body is emitting radiation. And I call it as E lambda divided by EB lambda, that's equal to emissivity lambda. Okay. Okay, so I talk about all these kinds of emissivity. Emissivity lambda, directional emissivity, spectral emissivity, meaning at wavelength, and normal emissivity perpendicular to the surface, all this. So are you clear with emissivity? Emissivity is the ratio of radiation emitted by a real surface in general terms to that of emissive power of a black body, and both are maintained at the same temperature. This is the condition. Then both shall have the same area. Okay. So, and again, a specular reflection and diffuse reflection. Reflection, what do you mean by that? Okay, incident radiation is coming. Incident radiation is coming and falling on a surface. Now, when radiation falls on the surface, three things can happen to this radiation. One, radiation will be absorbed by the surface if it is a perfect black body. All the radiation falling will be absorbed by the surface. If it is a transparent plate, now radiation will escape through this material, which is transparent. And if it is opaque, all the radiation falling in it is reflected, even if it is not absorbed. Now, we talk about the surface nature that it has some reflection capacity. Maybe some radiation is falling on it. Of that, some radiation is reflected. If not entire thing, some portion of it is reflected. Now, every surface will have a normal, and with the vertical, if you know the incident angle, theta, the reflected angle will be a mirror image of the incident radiation, and it will be at the same angle. This is called specular reflection. Perfectly a mirror image. Now it's coming here and it's going. Now, if there is another surface, which is slightly different from this, incident radiation is falling on it. The radiation falling on it will be reflected again, even by this. But the only thing is, they reflect it in a different way. That means, in all directions it is reflected. Meaning, it is not a mirror image of that. It is coming here, it is not going back. Some part of it may be in the same mirror image direction, but it also reflects in all other directions. So therefore, the radiation falling can be either reflected as a mirror image, or it can be diffused in all directions, and that part of it which is getting diffused, I say it is a diffuse reflection, and that part of it which is perfectly reflected as a mirror image, I call it as specular reflection. Diffuse reflection and specular reflection. Gray body, real surface, there are two things. Anything other than a black body can be a real surface or a gray body. Gray body is slightly different from a real surface. What is gray body? The monochromatic emissivity of a gray body is constant. Meaning, for a gray body is not a black body. If it is a gray body, its emissivity is always less than 1, because it's not a black body. Emissivity is always less than 1. This emissivity of a gray body, if you find it at different wavelengths, you find emissivity of a gray body at 0.1 micrometers, 0.2 micrometers, 0.3 micrometers. Wherever you find, the emissivity is the same. Say the emissivity of the gray body is 0.7, you find it at all wavelengths. So, monochromatic emissivity of a gray body will be more or less constant, whereas for a real surface, epsilon lambda varies from wavelength to wavelength. And this is very standard, slide, every one of you know. Of the incident radiation that's falling on it, some part is reflected, some part is absorbed, some part is transmitted. And there can be nothing else. Of the incoming radiation. So, based on absorption, the radiation may emit radiation. The surface may emit radiation. Please don't get confused. Okay. The incident radiation is falling on the surface. Some part of it is absorbed. Some part of it is allowed to pass through. Some part of it is reflected. This is reflected radiation. Meaning what? The incoming radiation content is not changed. It is positively reflected. Incoming radiation is not changed. It is positively reflected. The wavelengths and all will be that of the incoming radiation. Whereas upon absorption of the radiation, then temperature perugutundi. when the temperature increases, they emit radiation, right, by virtue of the surface temperature. This is emitted radiation. This emitted radiation is altogether different from reflected radiation. If we talk about non-black body, anything other than a black body, you find two amounts of radiation coming out of it. What are the two? One is emitted by virtue of its surface temperature, and the surface temperature ఉంది కాబట్టి అది కొంత రేడియేషన్ ఎమిట్ చేస్తుంది. ఆ ఎమిటెడ్ రేడియేషన్ ఏంటి? ఇట్ షుడ్ బి ఇన్ ఎ లాంగ్ వేవ్ ఫార్మ్ థర్మల్ రేడియేషన్. అలా కాకుండా ఇన్కమింగ్ రేడియేషన్ ఉంటుంది. ఆ సర్ఫేస్ మీద ఎక్కడి నుంచి రేడియేషన్ పడితే దాంట్లో పార్ట్ గానీ మొత్తం కానీ రిఫ్లెక్ట్ కావచ్చు. So if any real surface, when you are talking about, two kinds of radiations come out of the surface. One is the emitted radiation, the another one is reflected radiation. Don't get confused. Reflected radiation will have the characteristics and properties of that of incoming radiation. Emitted radiation will be, based on the surface temperature and whatever the Planck's law says, whatever Wien's displacement law say, and they follow with the wavelengths. Okay, so there is a big difference between reflected radiation and emitted radiation. But ultimately, there can be only three parts. If G is coming, rho times G is reflected, alpha times G is absorbed, and tau times G is transmitted through. The absorptivity, reflectivity, and transmissivity are all given as ratios. What is absorptivity? Absorbed radiation to that of total radiation incident on it. Reflected radiation, part of the radiation reflected divided by total radiation incident, and part transmitted divided by the total transmitted. And in any case, alpha plus rho plus tau should be equal to 1. ఎందుకంటే G is coming, when G absorbs, G reflection, G transmission. It should be sum of that. So you go by these ratios. Alpha plus rho plus tau is equal to 1. And for opaque surfaces, opaque and which cannot allow any radiation to pass through, tau is 0. So alpha plus rho is equal to 1. And for a white body is a perfect reflector, opposite to that of a black body. Okay, it's again an ideal surface. For a white surface, rho is always equal to 1 because it reflects everything that's falling on it. For a black body, alpha is equal to 1. For a perfectly absorbing body or a black body, alpha is equal to 1. And when alpha itself is equal to 1, rho and tau are 0. When rho is equal to 1, alpha tau are 0. That's all. Okay. And Kirchhoff's law talks about equilibrium conditions. Under equilibrium conditions, the emissive power of a surface is equal to absorptivity of a surface. It's a simple derivation there. Any standard textbook can give you. Emissive power of a surface is equal to absorptivity. Emissivity is different, absorptivity is different. What is emissivity? Capacity of a material to emit radiation to that of radiation emitted by a black body. And when you're comparing how much it can emit as compared to the black body. What is absorptivity? Absorptivity is totally different. Amount of radiation that's falling on it, and of that, how much is absorbed? See, if say 100 kilowatts is falling on a surface, if the material is absorbing 60 kilowatts, absorptivity is 0.6. Okay, so amount of radiation absorbed divided by amount of radiation falling on the surface. These two appears to be not connected. Kirchhoff's law, not electrical Kirchhoff's law, radiation Kirchhoff's law. Connect that, and it says monochromatic emissivity is equal to monochromatic absorptivity. And hereafter, don't get confused. Monochromatic means at that particular wavelength, at a given wavelength. Monochromatic emissivity is equal to monochromatic absorptivity. Directional emissivity at a particular wavelength is equal to directional absorptivity at the same wavelength. Okay. Now we talk about view factor or a shape factor. Okay, what is it? View factor and shape factor. But basically, you all have understood that radiation heat exchange is between surfaces. Radiation heat exchange, irrespective of the surface temperature, just now we have seen, we have discussed, irrespective of the medium separating them, they still can exchange heat, right? Now the question is, look at this. Both my hands are facing, palms are facing each other. Now let me say both are at two different temperatures, assume. Now radiation is emitted by this palm. Right now, we have discussed that radiation from a surface can be directional, can be wavelength specific, etc. Let me say this radiation is almost close to a black body. Em cheppan black body ante meeku, okay, black body is one which emits radiation in all the directions, right? In all the directions. Now, okay, I'll close it and then okay. Okay. Now let me say I have two surfaces facing each other like my palms. Now this surface is capable of emitting radiation in all these directions. In all these directions. Okay. Now, when radiation is capable of emitting in all these directions, surface 1 I call it, surface 2 I call it. Look at it, the way I have drawn it, entire radiation leaving surface 1 is not falling on 2. Isn't it? Entire radiation leaving surface 1 is not falling on 2. Some of it is escaped. Some of it is escaped here. Meaning, it is emitting radiation whereas it is not reaching the surface 2. So is the case with surface 2. Surface 2 also, it emits radiation whereas, it is escaped. Some part of it. Now, I say, it is, whenever I talk about view factor, it is the fraction of the radiation intercepted by the second surface of the total radiation emitted by the first surface. Meaning, if this is emitting 10 kilowatts of energy, and then this is absorbing, this is intercepting. Forget about whether it is absorbing or reflecting. What falls on it? When I said intercepting, దీని నుంచి వచ్చినది దీని మీద ఎంత పడుతుంది, పడిన తర్వాత ఏమవుతుంది, it can be absorbed or it can be reflected, it can be anything. Okay, పడిన తర్వాత it can be absorbed, it can be reflected, it can be anything. So now, what am I saying? దీని నుంచి how much of radiation is coming from the surface and how much is intercepted, how much is falling on it. If 10 kilowatts is emitted by this, only 6 kilowatts are falling on it. I say view factor from F, we call it F1 to 2. Shape factor, the symbol that we'll be using is F. F1 to 2. And 1 into 2 మీదకి వెళ్ళే radiation is only absorbed or when falling only 6 kilowatts of the total 10 kilowatts. That means F1 to 2 is equal to 0.6. This is called the view. Similarly, because the two parallel plates identically similar, now this should also be 0.6. From 2 to 1 should also be 0.6. But it is not guaranteed. But it is not guaranteed. Why is it not guaranteed? If this surface is different, and if it can emit radiation in a different way, I mean angular emission is more for this, then more amount of radiation escape, only less amount of radiation travel towards it. So, if two are identical, two are placed, F1 to 2 cannot be equal to F2 to 1. It depends on the surface properties, radiation properties, and the geometry. Okay. So, right now, what did I say? I have defined you what is shape factor F1 to 2. How much of radiation leaving 1 which is intercepted by 2? Simple. It's a shape factor. How much of radiation leaving 2 falling on 1 if it is F2 to 1? But majority of the cases, or as a rule, F1 to 2 need not be equal to F2 to 1. May be equal in some cases. May be equal in some cases. Where, in which cases, these two surfaces are identical. They have same properties, same radiation emission characteristics, same emissivity, same absorptivity, then this, how much is going from this and falling on this, how much going from this and falling on this will be same. And again, let me explain. Let me explain that three cases. One, let me say, yeah. Let me say, this is surface 1, this is surface 2. This is surface 1 and this is surface 2. Now, some radiation is emitted from surface 1 and it should go, the dome is surface 2, flat plate is surface 1. I'm sorry, just I'm not concentrating. So, surface 1 is emitting radiation, it's falling on 2. Okay. Now, 2 emits radiation, falls on 1. Now, you tell me what is F1 to do? What is F1 to do? Any radiation falling on 1, coming from 1, should definitely, because it's completely covered by dome. In any direction it is emitting radiation, it should be completely received by surface 2. F1 to 2 should be equal to 1. Meaning what? Any amount of radiation leaving surface 1 will automatically fall on surface 2, because that is the orientation of the surfaces. And that's where, when I talk about shape factor or view factor, the geometries of the two exchanging surfaces are very, very important. In this case, of a flat surface bound by a hemispherical bowl on top of it, any surface that is leaving 1 is going to fall on surface. Okay? Any surface leaving 1 is going to fall on surface. There is no doubt about it. Now, would you say F2 to 1 is equal to 1? Is it the question I am asking? F2 to 1 is it 1? The same configuration. This is true. Now, at the first instance, it may appear F2 to 1 is also equal to 1. Why? You thought anything that is coming, it's a closed enclosure. But you're forgetting. You're forgetting one thing, that because of the nature of the surface, the radiation emitted in this direction is not falling on 2, whereas it's falling on its own surface. It's not falling on 2, it's falling on its own surface. So that means what? Of the radiation leaving surface 2, only a fraction of radiation is falling on 1. Remaining, where is it going? It is being absorbed by its own surface. So, F2 to 1 is always less than. F2 is always. Okay? So, always it is said, when one surface is interacting with n surfaces, okay, when one surface is interacting with n surfaces, then it is interacting with only n surfaces, nothing else, nowhere else radiation is escaping, then F1 to 1 plus F1 to 2 plus up to F1 to n should be equal to 1. Meaning what? Radiation emitted by surface must be falling on its own surface. And it may also be falling on n number of other surfaces. If surface 1 is interacting with its own surface and with n another surfaces and with no other surface other than this n, then sum of all the shape factors. Meaning, I'll once again say. If I have a surface like this, okay, if I have a surface like this is 1, this is 2, this is 3, this is 4, this is 5, let me say. Is there F1 to 1? Meaning, any radiation, if it is perfectly a horizontal flat, is there F1 to 1? Radiation leaving 1, in whatever direction will it fall on 1? No, it will not fall on 1. F1 to 1 is equal to 0. And then, radiation emitted without escaping anywhere else is only falling. Radiation leaving 1 is only falling on 2, 3, 4 and 5. What is that say? Summative theory say F1 to 1 In this case, it is 0 plus f. There is chance that 1 is falling on 1 itself. If this is surface 1, radiation emitted will fall on it. If this is surface 1 and if the radiation is emitted outside, nothing falls on it. F1 to 1 is 0. But the same configuration, if radiation exchange is inside, F1 to 1 is there. If it is outside, F1 to 1 is 0. So F1 to 1 plus F1 to 2 plus F1 to 3 plus F1 to 4, okay, plus F1 to 5 is equal to 1. And it's interacting with only these 5 surfaces. Ingekada slipped out like radiation. Then the summative theory holds. By now you must have understood, okay, if it is a spherical enclosure, F1 to 1, if at all, if there is nothing to intercept, is equal to 1. Anything that is emitted inside is going to be intercepted by itself, okay, if nothing else is intercepting it. So you have seen, I've talked to you about summative theory. Shape factor is something about orientation of the surface. Okay, Fij, the fraction of radiation leaving the surface I that strikes the surface J or intercepted by surface J, and view factor ranges between 0 and 1. Meaning what? When is it 0? When is it 0? Okay, when this surface is emitting radiation only in these directions, this is 2, and if the surface 1 is not emitting any radiation in the direction of 2, nothing is falling on it, F1 to 2 is 0. F1 to 2 is 0. Or it is not in the scope of it. I said F1 to 1 is 0 in this case. Okay. We've discussed. If this is 2 surface, if it's emitting radiation outside, F2 to 2 is 0. And this is inside, F3 to 3 is not equal to 0 because something is intercepted by its own self. And 2 concentric spheres, when the inner sphere emits, it's all falling on outer sphere. Whereas when outer sphere emits, some of it may not be falling on inner sphere because the radiation emitted may be reaching back to the same surface too. So F1 to 2 is equal to 1, F2 to 1 is not equal to 1. F1 to 2 is equal to 1. F2 to 1 is not equal to 1 because some of the radiation may escape falling on 1 but fall on its own surface. So in such case, F1 to 2, F2 to 1 plus F2 to 2 is equal to 1. What did I say? Do you want me to write it? 1 and 2, F1 to 2 is equal to 1. Meaning everything that leaves is bound to fall on 2. F2 to 1, F2 to 1 is not in this direction, it can escape. It can escape. So F2 to 1 plus F2 to 2 is equal to 1. Because something leaving 2 may fall on 1, may also fall on 2. No other possibility. Okay. The view factor has proven to be very useful in radiation analysis because it allows us to express the fraction of radiation leaving a surface that strikes the another surface. Okay. So remaining things we need not discuss right here. And how do you find out the shape factor? For some of this, flat plate 1 to 1, I said 0. Any inner sphere, inner circle radiating into outer circle, it is 1. So for some of the standard configurations I have given, for any complex, 2 parallel plates, short parallel plates, like I said my 2 palms, though it appears they both are seeing each other, and if there is some distance between them, then there is a scope of radiation leaving the surface. It can be nearer, it can be farther. So that's how it goes. So depending on the distance, depending on the orientation, depending on the geometry, you can find the shape factors for various surfaces. The geometrical solutions are given for you. Okay. And the reciprocity theorem, finally, the summative theory I have told you. F I to I plus F I to j I to 1 plus I F I to 2 plus up to F I to n j is equal to 1. Sum of all the shape factors with which a particular surface is interacting should be equal to 1. The reciprocity theorem is A1 F1 to 2 is equal to A2 F2 to 1. This is very important. What is A1 is the surface area of first surface. What is F1 to 2? Whatever is leaving from surface 1 falling on 2. A1 F1 to 2 is equal to A2 F2 to 1. So the shape factors are inversely related to their areas. Okay. And some of the rules you can go how you measure the shape factors. Okay, this is crossed string method is described. Probably you will not use this in gate examination. And this part of this is very important for you to solve problems. And tomorrow morning, please don't forget, I start the class at 11, finish by 1. I'll explain this radiation networks from a black body and a real surface, and also go through some of these problems. Okay, thank you very much.